So we'll start with Thevenin's theorem today. Uh, so in the last session we did superposition theorem and we saw these theorems are only applicable to linear circuits first of all, and how in superposition theorem we can actually see the contribution of each and every independent source and find out the net contribution of all the sources together as well. With Thevenin's theorem what we do is most often what happens is that we are only focused upon some part of the circuit. Fine. Say for example, you have a residential load. आपके पास you may have a heater, blower, or a bulb or a fan. If we are talking about resistive loads mainly here, we'll be talking about linear circuits only for the time being. Uh, if we have a load that is resistive in nature, a bulb or a heater, what happens is we are only concerned with how much current is flowing through this bulb or how much voltage is across this bulb, and we are not concerned with the rest of the circuit. Fine, we are not concerned with what is current or what is voltage across any other part in this circuit. We are only focused upon our load, and we want to find out what is the voltage or what is the current flowing across this load. Fine. So you may have a network. We are talking about linear systems only, and there is a load connected to this circuit network. Fine. We only want to find out what is the voltage across this load. We want to find out what is the voltage across this load and what is the current flowing into this load, and we can also find out what is the power flowing in this load. So what does Thevenin's theorem state is that we can replace this entire network, entire circuit network, that may consist of a voltage source or a current source or a combination of voltage source and current sources. There will be a number of resistances there. Fine. So this circuit network can consist of number of voltage sources, current sources, or resistances. Say for example you are taking a residential network. uh, आपके घर पे supply पहुंचती है, that can be considered as a voltage source. Then internally you have a number of you have wires connected that have their own resistances. There are some other elements connected. Say for example, you have a geyser, you have a heater, you have a blower, you have a bulb. All of these are functioning. All of them are functioning at certain instant of time, but you are only concerned with what is the voltage, what is the current across this bulb. All these other loads, all these other elements in the circuit, a heater, a blower, or a geyser, they can be considered as resistive loads as well. But we are not concerned with that part of the circuit. So it can be clubbed as a circuit network, and we are only concerned with one portion of the circuit, that is a bulb. And we want to find out what is the voltage or current across and flowing into this bulb. Fine. तो ये जितना भी बाकी network है, we'll club that together. That portion of the circuit network will be separate and our load is separate. What we can do is, Thevenin's theorem states that we can replace this entire circuit network by a single voltage source in series with the resistance. Fine. And then this is your load. This is your variable load that you're actually focusing on. You're only bothered with this particular load, that is the variable load RL. Rest of the circuit, what we are doing is we are clubbing that all together, and that can be converted into one voltage source and one resistance. This voltage source that we find out is known as the Thevenin's voltage, and this resistance that we find out is known as the Thevenin's resistance. So Thevenin's theorem states that a linear circuit can be converted and replaced by an equivalent circuit which has a voltage source in series with the uh, fixed resistance. This voltage source is known as the Thevenin's voltage. That fixed resistance is the Thevenin's resistance, and that will then be in series with the load resistance that across which actually we want to find out the value of current or the voltage value. So it all of this complex circuit will boil down to a simple circuit which has one voltage source and two resistances in series with each other. Fine. So you can have a circuit like this. This can be a network of a circuit. It has a number of resistances R1, R2, R3, R4, R5, R6. It has a current source somewhere. It has a voltage source somewhere. And there is then this resistance RL that is actually our load, and we are only concerned with the voltage across this load and the current flowing into this load. Now since this load resistance is variable here, so uh, the voltage and current flowing into this resistance will actually change. It's I have set the permissions to auto admit. They can join directly. There may be network connectivity issue on their end. I have set the permissions to auto admit. So this entire portion of the circuit can then be replaced simply by a voltage source in series with the resistance VTH in series with RTH, and then you have your load resistance. Now why do we do this? We are marking our load resistance here as variable. So since this resistance is variable, since our load is variable, say for example यहाँ पे हमारे पास एक blower है, so we can actually vary the resistance here so that we can change the temperature settings. Fine. So if our load is variable in nature, this current flowing into this resistance, into this IL and VL, that is the voltage across this resistance, and the current flowing into this resistance will also change. If RL decreases, IL may increase and VL will accordingly vary. As see, if RL increases or increases, IL may decrease and VL will vary. So this IL we have to calculate. We are only focused with calculating current flowing into this load and voltage across this load. Since our load is now variable, so current and voltage flowing into this load is also changing as we change the resistance of this load. Now we cannot solve this circuit every time. We cannot हमें अगर ऐसे circuit दिया जाए तो we'll have to every time we'll have to solve this entire circuit, find out what is the current and what is the voltage across this resistance. Instead of solving this every time, what we can do is we can simply replace this circuit by an equivalent Thevenin's equivalent. That equivalent circuit only has one voltage source and one resistance in series with this variable load. Now it's easy for us to calculate current flowing through this resistance or voltage across this resistance once VTH and RTH is known to us. We can easily do this. We do not need to solve this complex circuit every time, we can easily solve its Thevenin's equivalent and find out the voltage or the current flowing through this particular load resistance. Fine. So I will write this here. So what does Thevenin's theorem state? So Thevenin's theorem states that a linear electric circuit can be replaced by an equivalent electrical circuit network can be replaced by an equivalent circuit consisting of Thevenin's voltage in series with the Thevenin's resistance and load resistance. So an electrical circuit, a complete network of electrical circuit. So for example, we are saying for some time, let's assume that a power system is a linear network. Fine. So at a generating station, we have the voltage. Then across the transmission line, that voltage is being transmitted to the distribution stations, to the substations. आपके घर के बाहर मोहल्ले में एक ट्रांसफार्मर लगा हुआ है जहाँ से फिर आपको you are getting the electrical supply, and in between there are a number of other households that are connected to this electrical network. So let us assume that all these electrical networks can all those other households can be considered as resistive elements. Your generating station has a voltage source, so all of that network from the generating station up to your household can be considered as a lumped network. We can replace all of that by a simple voltage, that is VTH, in series with resistance RTH. Fine. And then your part of the household will form your load resistance, and you are only concerned with what is the amount of voltage or what is the amount of current flowing into your house. Fine. You are not concerned with what is the voltage or current with any other household or with in your neighborhood. Fine. So that entire network can simply be replaced by just one circuit having a Thevenin's voltage in series with RTH in series with their load resistance. So it now becomes easier for us to solve for the voltage and current flowing into your household. आपके घर में भी load change होता रहेगा, so your load resistance is also changing. So every time the voltage and current will change, that's actually flowing into your household. But you cannot keep on solving the entire network, entire that huge network every time. So that's simply replaced by an equivalent circuit, that is the Thevenin's equivalent circuit. So that's what the Thevenin's theorem states. Now, how to actually find out this Thevenin's theorem? Now, there are two cases. Both the cases, there will be procedure to. Yes, sir. Yes, sir. Your voice is breaking. So let's continue. So we have the Thevenin's theorem, statement of the Thevenin's theorem. Now, how to solve for the Thevenin's theorem? We'll be discussing two cases. One is with without dependent sources, and then will be with dependent sources. What we can have is, let's say for example, we have this network of circuits. So RL is the load resistance. You are only concerned with what is the current flowing into this load and what is the voltage across this load resistance. Fine. So the steps that we have to take to find out the Thevenin's voltage and the Thevenin's resistance. So step one, turn off all independent sources. So this is case number one, which is without dependent sources. There is no dependent source in this case. So you have to turn off all the independent sources. Uh, so by turning off, as I said to you last time also, we have to make the voltage equal to zero. We have to make current equal to zero. Voltage equal to zero means short circuiting the voltage, and current equal to zero means open circuiting that particular terminal. So this circuit will look something like this. Once we turn off the circuit, turn off all the independent sources. करंट सोर्स तो आपकी ओपन हो गई. You have R1, you have R2, you have R3, and then you have RL. That is actually your load resistance. So turn off all independent sources and you have to actually open the load as well. So this part of the circuit is now open. So with this in mind, calculate the equivalent resistance so from the open circuited end, look into this circuit and find out R equivalent. So whatever value you will be getting, that will be actually R Thevenins. Fine. So you have that. You had this circuit. You had two independent sources. One was a voltage source and one was a current source. So you have to turn them off. Voltage source turn off means you have to short circuit it. Current source you have to open circuit it. Now only resistances will be left in this circuit, and the load that actually is our primary focus. We have to open that load as well, and we have to look into this circuit from that open end and find out the equivalent resistance. So what you can see is that R3 is actually R equivalent is actually equal to what? It is R3 parallel R2 and it is parallel to R1. So all these three resistances are actually in this case parallel to each other. Whatever be the case, you have to find out the equivalent resistance, and that equivalent resistance will be your Thevenin's resistance. So you have actually found out the Thevenin's resistance. Now you need to find out the Thevenin's voltage. So for that, step 2 is uh, open the load with all independent sources intact. Uh, so all the independent sources that were in the circuit, यहाँ पे एक voltage source था, you had the resistance R1, R2, and you had the current source, you had the resistance R3, R1, R2, R3, and you have opened the load. So what you have to do in this case is now there will be a voltage across this end. Find the find the voltage across this open circuit. So this voltage that will be across this open circuit VOC will be nothing but the Thevenin's voltage. So once you have these Thevenin's voltage and Thevenin's resistance, step 3 will be construct the Thevenin's circuit equivalent of the original circuit. So you have now you have calculated RTH, you have calculated VTH. Now construct the Thevenin's equivalent circuit, that is simply VTH in series with RTH in series with your load resistance. So now you may be asked to find out current or voltage across this particular resistance. So you can do that now easily. So actually दो ही steps हैं. One step is you have to open the load resistance first of all for both the cases. Uh, Turn off all the independent sources, find out the net equivalent resistance, that will be your Thevenin's resistance. Now with all the sources intact, find out the voltage across that open end. That voltage across that open end will be the Thevenin's voltage. So once you have both VTH and RTH, you can uh, redraw your circuit as including the load resistance as well from your original circuit. So let's do one example. So find the Thevenin's equivalent circuit then find current through RL for RL equal to 6, RL equal to 16 and RL equal to 36 ohms. So this is your circuit here. You have a voltage source, you have a resistance of 4 ohms, you have a resistance of 12 ohms. So this is a very important theorem that you have to remember. This is your load resistance. So across these two terminals VAB, you have to actually find out the Thevenin's equivalent. That means this entire network that we have here needs to be replaced by VTH and RTH, and then we have to incorporate back the load resistance RL. So we have to perform the analysis. So step 1, open the load resistance and turn off all independent sources. Turn off all sources and open RL. So हमारा circuit क्या होगा? 32 volts will be short circuited. We have 4 ohm resistor here. We have 12 ohm resistor here. 2 ampere will be open circuited. We have 1 ohm resistor here. So we have to find out R equivalent by looking into this circuit from this end. Fine. So what will R equivalent be in this case? 4 and 2, 4 and 12, they are in parallel with each other, and that those two resistors are then in series with the 1 ohm resistor. 4 and 12, they are in parallel and then in series with 1 ohm resistor. So 4 cross 12, 48 by 16. So this is 4 ohms. So R equivalent हमारा 4 ohms है. That's actually now RTH. So this is step number 1. Now step number 2. 32 volts AC, 4 ohms intact, 12 ohms, 2 ampere current source here, 1 ohm resistor, and this end is open circuit. We need to find out VOC, that is the voltage across this open circuited end. So now you can actually apply mesh analysis and find out this open circuited voltage. So you have actually only two meshes, mesh 1 and mesh 2. Let current this be I1, this current be I2. So by applying KVL in mesh number 1, we have 32 is equal to 4I1 plus 12I1 minus 12I2. By applying KVL to mesh number 1, so which implies 32 is equal to 16I1 minus 12I2. From mesh number 2, I2 is equal to what? It's simply equal to minus 2 amperes. So substituting this back here, which implies I1 is equal to 0.5. Now what will VOC be equal to? Since this resistance is, since this end is open circuited, no current is flowing here. That means as if this resistance is not there in the circuit. So VOC is the voltage across this 2 ampere current source, or you can say simply VOC is the voltage across this 12 ohm resistance. Fine. So VOC here is now equal to what? Open circuited voltage is the voltage across this 12 ohm resistor, that is 12 into uh, इसकी जो resistance into current that is flowing through this resistance, that's I1 minus I2. 12 I1 is 0.5 minus I2 is minus 2, that becomes plus 2. 12 into 2.5, that is 30 volts. Fine. Open circuited voltage VOC, since 2 ampere, 12 ohms, they are all in parallel. 1 ohm is open circuited, that means there is no drop across this, no voltage drop across this 1 ohm resistor. So जो भी voltage 12 ohm resistor के across होगी, that will be across the open circuited end as well, and that we are getting is equal to 30 volts. So VOC or VTH you can say now is equal to 30 volts, and RTH is equal to 4 ohms. So we can now redraw the circuit. We have now a simple 1 ohm के अक्रॉस वोल्टेज ड्रॉप इसलिए नहीं होगा क्योंकि ये एंड ओपन सर्किट है, यहाँ से करंट जो फ्लो हो रही है वो जीरो है. अगर करंट जीरो है तो वोल्टेज ड्रॉप होगा 0 into 1, that is 0. क्योंकि अब यहाँ पे कोई वोल्टेज ड्रॉप है ही नहीं, तो यहाँ पे जितनी भी वोल्टेज इस पॉइंट पे वही वोल्टेज VOC के अक्रॉस भी होगी। तो अब हमारे पास VTH मिल गया। VTH we have found is equal to 30 volts. RTH we have found 4 ohms. And now we can place back our load resistance, that is RL. Now we have to solve for, we have to find the current I that is flowing through RL for 3 different cases. For RL equal to 6 ohms, RL equal to 16 ohms, RL equal to 36 ohms. Now if you did not have this Thevenins equivalent, you would have to first place 6 ohms resistor here, find out what is the current in this circuit by solving this entire circuit. Then you have to put a 16 ohm resistance here, again solve the entire circuit. Then you have to put 36 ohm resistor here, again solve this entire circuit. So it would have become tedious for us for every time to see what is solving that big network. With this simple equivalent circuit, Thevenin's equivalent circuit, now we can easily find out our the current I flowing through RL. Fine. So I किसके बराबर होगा अब? It will be simply voltage, that is 30 divided by 4 plus RL. So for case number 1, I will be 30 divided by 4 plus 6, that is 3 amperes. For case number 2, it is 30 by 20, 2 by 3 or 3 by 2. And I equal to 30 divided by 3 by 4. ठीक है, 0.75 amperes. We can now easily find the values of currents flowing through this circuit. To this, find I in this circuit by replacing it by its Thevenin's equivalent circuit. Fine. We have to find the Thevenin's equivalent circuit of this and then find out the current I that is flowing through the 1 ohm resistor. So you will find out this circuit. You will have VTH. हाँ, लोड रेजिस्टेंस उसमें यहीं से दिया हुआ है, that is 1 ohm. अब यहाँ पे वेरिएबल नहीं है, it is fixed 1 ohm, but you have to find out current by replacing its by providing its Thevenin's equivalent circuit. So you have to tell me the values of VTH and RTH. That is it. करना प्रोसीजर वही है. Open the load resistance, that is open this 1 ohm resistor. Turn off all independent sources. Find out R equivalent. Yes. No. No. RTH 3 ohms है. When you will open circuit this 6 and 6, they will simply be in series 12 ohms, and then they will be in parallel with 4 ohm resistor. 12 into 4 divided by 16, that is 3 ohms. So RTH आपका 3 ohms आ रहा है. और VTH 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 is coming out to be 6 volts. VTH is coming out to be 6 volts. When you will solve, yes, when you will solve this circuit, so you have a 12 volt voltage source, you have a 6 ohm resistor here, you have another 6 ohm resistor here, you have a 4 ohm resistor here, and this end is open circuited, and you have a 2 ampere current source here. Now if you will apply the mesh analysis, since this current source is present in between two meshes, so you can actually consider this as a super mesh then. If current I1 is flowing here, current I2 is flowing here, from the super mesh we'll get the equation 12 is equal to 6I1 plus 6I2 plus 4I2. Fine. So ये एक equation हो गई, and also from this middle this current source I1 minus I2 is equal to 2 amperes. 12 is equal to 6I1. हाँ एक मिनट, 6I1 plus 10I2, ये आपकी एक इक्वेशन हो गई. I2 minus I1 is equal to 2 amperes, ये आपकी दूसरी इक्वेशन है. I2 is equal to 2 plus I1, so you can substitute it here. 12 is equal to 6I1 plus 10, 2 plus I1, 6I1 plus 20 plus 10I1, 16I1 is equal to 12 minus 20 minus 8I1 आपका minus 8 by 16 minus 0.5. So I2 is 2 minus 0.5, that is 1.5. So I1 is minus 0.5, I2 is minus 1.5. 1.5. So I2 आपका 1.5 है. तो जो आपकी वोल्टेज है यहाँ पे VTH, that is the voltage across this 4 ohm resistor, that will be 4 into the current flowing through this resistor, that is 1.5. 4 into 1.5, you are getting 6 volts. Mute your microphone. Okay, to this 3 ampere current source, 10 ohm, 16 ohms, another 10 ohm here, 24, 24 volts. This is 24 here. This is 5 ohms. This is your open end terminal AB. Fine. So you have to find out VTH across this open end terminal. Fine. So you have to find out VTH. You have to find out the equivalent circuit, Thevenin's equivalent circuit, RTH across this open end terminal, that's AB. Find out VTH and RTH for this circuit. No, RTH will not be 4. RTH, yes, it is 20. So you have to open the current source, you have to short the voltage source. 3 ampere source तो गया, 24 volt short हो गया, 10 और 10 आपके series में आएंगे, so that's 20 ohms. 20 ohms in parallel with 5 ohm resistor. Fine. So this circuit will look something like this. ये आपका 10 ohm resistor हो गया, 10 ohm resistor हो गया, 5 ohm resistor, 16 ohms. 10, 10, 5, 16. So 10 and 10, 20. Parallel with 5 is 4 ohms. 4 and 16 then are in series. So you are getting RTH equal to 20 ohms. Then find out the open circuit voltage VO, the Thevenin's voltage. Yes, VTH, how much are you getting VTH? Huh? VTH, VTH will be negative, minus, no. Answer fractions में. Yes. VTH is minus 49.2 volts. You have one mesh, I1, you have another mesh, I2. यहाँ से तो कोई करंट फ्लो नहीं हो रही है, ठीक है. You have from the above mesh we can say directly I2 is equal to minus 3 amperes, and in this mesh by applying KVL you will get 24 is equal to 10 I1 plus 10 I1 minus I2 plus 5 I1. Fine. So I2 is already minus 3 amperes, that is known to you. So you can solve that equation to find out the value of I1. So once you have I1 and I2, then you can find out the value of VTH, the open circuit voltage. That open circuit voltage will be the voltage at this point. हाँ यही सवाल होंगे Thevenins theorems में. You will have to find out Thevenins equivalents of different circuits. You can try this at your places. ये एक अच्छा खासा सवाल है. सब कुछ दिया हुआ है. Fine. So you have to find out Thevenins equivalent circuit across points A and B. ठीक है. तो A and B is the open circuited terminal. बीच में ये बाकी network है. You have to find out Thevenins equivalent circuit across the terminals A and B. मैश एनालिसिस मैंने आपको बताया, एक मैश ऊपर है, एक मैश नीचे है. ऊपर वाले मैश से I2 इज डायरेक्टली इक्वल टू -3 एम्पियर्स, वो तो हो गया. नीचे वाले मैश में इक्वेशन इज सिंपल. 24 इज इक्वल टू 10I1 प्लस 10I1 माइनस I2. एक हाँ अभी दिखाता हूँ. प्लस 5I1. ठीक है. तो ये तो KVL in loop 1, you will get this equation. From this mesh directly I2 is equal to -3. Substitute this here, you will get the value of I1. ठीक है. आपको voltage across this 5 ohm resistance will be 5I1, but ये जो यहाँ से voltage drop होगा because of current I2 flowing through it, you will have to subtract that, find out the voltage at this point. That will be the voltage across this terminal. ये आपका दूसरा सर्किट है. You can try this, you can take your time, you can do this at your places. मैं इसका आंसर आपको बता देता हूँ. इसका RTH 10 ओम से, VTH 10 वोल्ट से. Fine. So that's all for today. ठीक, VTH भी निकालना है. Okay, I'm ending the session. So ये आप कर लो. अगर नहीं आता है तो हम फिर कल देख लेंगे इसको.